Today's video is about the lac operon, and it is very similar to our trip operon, except that it is flipped. Your trip operon was always on, and so we could turn it off. The lac operon is always off, so we can turn it on. And this version you see right here is the version that is from page 306 in your book. And right now, the lac operon is going to be in a state of being off because it only turns on, so turns on when lactose or galactose is present. So there's no need for it to be on if there is no lactose, because then it would be making a product that wouldn't be necessary. So being how efficient the cell is, this bacteria cell does not turn itself on until its environment changes. So this presence, okay, is your environmental change. All right, so now, same concept. This operon is a segment of the DNA of the bacteria. It has a gene for the regulator, and then it has a promoter region, and then the actual operator. And the RNA polymerase would like to move down this piece of DNA to do transcription and translation, but in normal circumstances, this red piece, this repressor protein, has it blocked, and that is the normal standard way that it is. Now, when lactose becomes available, the bacteria shifts into a different mode. And over here in the corner, this is where the shifting and the processing is going to happen. Our green dot here, looks like a little green pea, is our allolactose, which is a very similar form of lactose. And we're going to call him our inducer, okay? Because what happens is when he becomes present, he will be able to bind and fit perfectly into our repressor protein. And we know that when things bind to proteins, it changes the shape. So now that the shape is not correct, it cannot fit into our zone right here, which is our operator. So now RNA polymerase is free to continue and progress along that piece of DNA. And as she progresses along the DNA, she's going to do transcription. And transcription is going to go from the DNA to the messenger RNA, DNA to messenger RNA, DNA to messenger RNA. Now in our trip operon, our pieces, our genes were E, D, C, B, A. In our lac operon, our genes are Z, Y, and A, all right? So lac Z gets transcribed into a piece of messenger RNA with a start and a stop, and he makes this protein called beta-galactosidase, okay? And these are your ACEs. So ACE right here always means an enzyme. And then lac Y makes a piece of messenger RNA, start and stop, and it's going to make permease. And then lac A is going to be transcribed into a piece of messenger RNA and then translated into transacetylase. These all together, I'm going to zoom in on this so you can see my words. Okay? These three proteins that get made in translation by the ribosomes are together, they're all needed to break down lactose or allolactose. So these enzymes are only made when needed, and so we're back to our supply and demand, okay? And then so to fill in the blanks here, this operon is always off unless lactose is present, and that lactose turns it on. Okay, so what do you think is going to happen when all the lactose gets broken down? It'll be gone. There won't be any green dots. The green bubble helps change the shape of our repressor. So if there's no more green bubbles, our repressor is going to be now back to the correct shape, and this whole process will get blocked and it will be back off. Okay? So the main idea here today is all about operons. And what we want to remember, let me find my marker, zoom back out. Only in prokaryotes. They are clusters of genes or tandem jobs. Can turn them all on at once. Okay, so they're not separate. In a eukaryotic cell, all of those genes would be turned on and off separately, and so therefore you would not have clusters of genes. They also have a regulatory, okay, and in the trip, the regulatory gene is an inducer. It makes an inducer protein. But in the lac operon, the regulatory gene trip makes a repressor off, okay? The lac operon will make an inducer.